is here. Thanks. Okay. So, good afternoon. Yes, Rachel's not here, but she was a good girl. She went to the Lunar Highlands crust and visited the Stillwater, and now she's off in a geologic wonderland that is Yellowstone. So she found out she wasn't going to be able to give this, and so she just went down the hall and asked if I'd give a voice to some of the work we've been doing, and I'm happy to oblige. So, this is Bullialdus Crater. It's around 20 south, 20 west, right here down in Mare Nubium, about 61 kilometers in diameter. It's tapped material approximately 6 to 8 kilometers of depth in its central peak, and it's the Eratosthenian age. Okay, so Bullialdus for many years has been a particular interest because of its spectral characteristics, namely its central peak and its walls tend to have a noritic component, and its walls clinopyroxene. Carly did a study back in 1991 where she interpreted this as potentially being a layered mafic pluton. Then other studies since then have been taking a look at other possibilities, which include an impact through an old basalt, thin old basalt layer by Tompkins and Peters, or through a differentiated melt sheet from the Nubian impact. Work by myself took some theoretical mixing models and tried to take a little bit more rigorous analysis of this in a quantitative way, just a different way than before. And we found a range of compositions, particularly within the peak, but the main thing was there was this noritic component that was seen before by Tompkins Peters in previous work. Subsequent work trying to quantify MG number by myself and then Rachel, I found for the central peak there was a mean MG number around 70, and Rachel concentrating on that noritic component, perhaps the norite lithology in general, it seems to have found an MG number around 75 or a little bit greater. So Rachel's been using M-cube data, in particular color composites to begin with. Let's see if it'll pop up. One of the standard ones is where the red component is the 1 micron band depth, the green component is this 2 micron band depth, and blue tends to represent the highlands, and pyroxene in this particular composite tends to be yellow in these composites. So this is one that I'll be explaining. The other is a pyroxene composite where red is representing the 1.9 band depth. Green is integrated 2,000 nanometer band depth, and blue is the integrated 1 micron band depth there. In general, this tends to show the highlands as black. Low calcium pyroxene tends to show up as yellow, and high calcium pyroxene will show up as cyan. So the M-cube team gathered this incredible data set. You can look at it all day. It's just got deposits, very interesting geologic deposits popping out of the imagery. But in general, the characteristics of M-cube is about 85 spectral bands, 20 to 40 nanometer spectral sampling, about 140 meters per pixel during its 100 kilometer orbit. And it's got this unique spectral range for lunar spectroscopy going from about 0.4 to 3 micron wavelength range. The 3 micron wavelength is particularly important for the remainder of this talk, which I'll touch on in a little bit. Okay, so Rachel wanted to take a look at combining a few data sets. Two of them were M-cube data set, of course, and then the data set that came back from GRS for the Lunar Prospector. And where Boleotis is right here in M-cube data, and right over here in the thorium data. We'll take a closer look at this. In Clementine, here is Bullialdus. The central peak is outlined right here, so you can see it within the Lunar Prospector thorium data. Justin Haggerty, one of our co-authors, is actually doing some forward modeling, additional analysis of the Lunar Prospector thorium data, which he's hoping to, in a statistical way, constrain this, the distribution of thorium a little bit more compared to the initial thorium product. We're hopeful to see those results pretty soon. And here's the M-cubed data. Again, here is the color composite characteristics, where 1 micron is showing up in blue. So yellow in the central peak is characterized with noritic material. Mare basalt material has this combination of bluish to cyan to red around the outside and the ejecta blanket. And the black color, which I found really interesting around the rims, is interpreted to be a northsite. So here's a closer look. And here Rachel took a look at some of the spectra, which are pretty interesting. She took 3 central peak spectra up here. You can see the very nice noritic component, and then there's a more gabbroic component, or gabbronoritic component there. As well as she saw this very featureless, what can be interpreted to probably be in a north-citic composition in the peak as well. Now, what is particularly interesting about these, particularly because this crater is of so much interest because of its composition, is that around 3 microns, we suddenly see a little absorption out here, which we couldn't see with previous data sets. And we'll switch here. Between about 2.7 and 2.8 microns, we see an absorption that is typical of hydroxyl feature. And this is particularly unusual, I'm saying particularly a lot, in the context of Boleotis, because it's so far removed, it's more equatorward compared to where you might see these detections in previous M-cube data, closer towards the poles. So it's kind of out of left field. Rachel certainly didn't expect it. I know I didn't expect it. And so it's there. And so we're trying to figure out why and what it means for the geology. So we took a look at some other data sets just to try to put this hydroxyl feature into a little bit more context, namely the LROC NAC and LROC DM that was produced from the WAC mosaic. And so we pulled them, and Rachel brought them down and overlaid them. Now this is the north, looking from the north. So north is this way. We're looking down towards the south on the peak. And the hydroxyl feature's intensity is overlaid over these peak crests. What's really unusual is that it kind of is always just below the peak crests, and it usually corresponds with a more coarse rubbly material, which is a little bit more fresh than the surrounding. Bullialdus in general is a pretty immature crater, or crater peak, but these hydroxyl features, specifically the highest intensities, correspond with this rough material on the peak slopes. So M-cube also offered the advantage that it took a look at Bullialdus multiple times. And so initially, looking at this hydroxyl feature, we were wondering, well, could it just be an artifact? I mean, is it just specific to one optical period? But sure enough, it shows up in optical period 1B, 2A, and 2C1. So it's still there. So to kind of wrap up, the crux of this story is hydroxyls and Bullialdus, and it's typically it wasn't anticipated to be there, but it is, and it's potentially has implications for the geology in the central peak. Typically, hydroxyl is likely to be present in a thin superficial layer from interactions with solar wind with the lunar regolith. But we've taken a look at this with Bullialdus multiple times, and it's quite plausible that this may actually be contained within the actual minerals within the central peak of Boleotis. So highland soils in particular show stronger OH bands towards the poles on the moon, but those around the surrounding Boleotis don't show it at all. It's completely absent. They just show up in the central peak. So while the region surrounding Bullialdus is also enhanced in relative thorium to the surrounding region within Nubium, there's a particular hotspot that is actually corresponded with Bullialdus, and so we're doing additional work trying to resolve, is it within the crater, just off the side? Does it correspond with the central peak? We'll find out when Justin comes back with his results. But the bottom line is, right now, Bullio seems to correspond with this high thorium enrichment. So normal highland and north sites don't correlate with this thorium enrichment at all. So it lends you to believe, well, maybe this is potentially a creep-rich Mg or alkali sweet pluton. The deconvolved abundances that Justin is getting to this point are kind of starting to point to it being more consistent with an alkali sweet rock. And in Rachel's interpretation, it would lend her to believe that this might be more consistent with an Mg-rich pluton because the hydroxyl would have more time to concentrate. Now, when I say concentrate, that's a relative term. Whether this would actually influence the petrology of the deposit is still left to be determined. So I think that's about it. So further work is going on, and I'll take questions. Everybody's hungry. My stomach was growling.
Okay, well, we'll move on. Thank you very much. The last talk in this session is by